Welcome to Microlecture 6 on resonance basics and the curved arrow convention. We can't get too far in our understanding of drawing Lewis structures to realize that sometimes there is more than one way you can draw a Lewis structure. These different ways are called resonance forms of each other, and I just want to be clear that there is never going to be any difference in the connectivity of atoms between one resonance form and another. We are never going to make or break sigma bonds. A couple of other notes about resonance. It's not a process. Resonance forms are different ways that we can depict the actual molecule. And so the actual molecule actually exists as a hybrid of all the possible resonance forms. I'm going to teach you a method of curved arrow notation to push the electrons around to get from one form to another of resonance. Just know that it's not really a process. That means the molecule doesn't spend some of its time looking one way and some of its time looking another way and interconverts between the forms. Okay, so it's not a process. And the last thing here, we will use this double-headed arrow only for resonance, and we must use it to separate resonance forms from one another. So we're going to be using curved arrows to show electron movement, and it's important to note a couple of things. Only moving pi electrons rather, so that could be pi bonds, or electrons that are serving as lone pairs. And we are going to start the arrowhead where the electrons are and end the arrowhead where we want the electrons to now be. And that could be an atom or a bond. Okay guys, so let's practice. The curved arrows are shown for you on the left-hand side resonance form, and so all you have to do is follow those curved arrows and come up with the proper structure, and some details of the proper structure are already drawn for you. So this is a drill to just get used to using curved arrow notation, where the curved arrows have been actually provided for you. In the future, you'll provide them, but it's just a baby step along the way in learning how to push electrons around. So this oxygen still has two lone pairs sitting on it. Only one of the lone pairs was used to create this pi bond, which is right here. And then at the same time, electrons were moved off onto this carbon atom, leaving it with a negative charge, so that must be labeled. Notice that I couldn't have stopped pushing the electrons with the first curved arrow because there is a hydrogen atom sitting right here, and we know that, right? And so it's still there. And so if we had stopped pushing the curved arrows without moving the next pi bond over to the terminal carbon, then that carbon in the middle would have ended up with 5 bonds, which of course is a huge violation of the octet rule. So go ahead and pause the video and attempt these, and then come back and make sure you got it correct. So I'm going to push electrons into this bond to form a pi bond, but at the same time electrons were pulled away from this carbon at the end, so it now has only 3 bonds and a formal charge of 1. The carbon that is sitting at the end, the one that is right here with 2 hydrogens on it, it's now satisfied and has 8 electrons around it, so no more formal charge. Okay, so the next problem here has the lone pair of electrons on OH moving in to form a multiple bond. So new pi bond, oxygen to carbon, and the next pi bond over has deposited its electrons onto the carbon atom, giving it a -1 formal charge. And then the only other thing to consider here is that since this first resonance form was neutral, this new one must be neutral, and we have a -1 charge, so it turns out is balanced by the fact that this oxygen with 3 bonds and 1 lone pair has a +1 formal charge. That's going to be equally important with this next one here, where we're moving electron density away from a carbon atom. So we're generating a +1 formal charge on that carbon, which has 3 bonds now and no lone pairs. We've moved this the 2 electrons from the pi bond over 1. To create this pi bond here, carbon-carbon pi bond, and then the electrons in the carbon-oxygen pi bond are kicked off onto oxygen, generating a -1 formal charge on that oxygen atom. Great, so the next one is a nitro group, and the electron delocalization is from one oxygen all the way over to the other, so it's across these 3 atoms of the nitro group. Nothing regarding charge happens to the nitrogen, like no net change, because as we add electron density to it, we remove electron density from it. And the pi bond looks like it moves, but we want to think about resonance not in terms of bonds moving, but rather electrons moving. So the electrons on the negatively charged oxygen move in to create a pi bond between nitrogen and oxygen. And then the adjacent pi bond is broken, kicking those electrons off onto oxygen, which now has a -1 formal charge. Okay, so the next one is a carbocation. It's just off of a benzene ring. Remember, benzene rings offer lots of opportunity for resonance. But this question is just pointing to one of the resonance forms. So we moved electron density away from this carbon atom, moving the pi bond adjacent, and fulfilling the octet of the carbocation just off the ring. So draw in hydrogen atoms for clarity whenever you need to. There were only 2 hydrogen atoms there because the carbocation, and so those 2 hydrogen atoms, of course, are still sitting there. We can't move atoms around or make or break sigma bonds for resonance. So if it helps to draw in hydrogen atoms just to ensure that we haven't done any of that, then definitely do that. The next one, we've got a lone pair on nitrogen sitting, adjacent to a pi bond. So that's a red flag for the opportunity to do resonance. We're going to kick electrons in from the nitrogen atom, and then break one of the pi bonds in the ring and kick those electrons out onto a carbon atom. Of course, we generated a negative charge here, and the original resonance form was neutral. So remember to ensure that all of your resonance forms have the same net charge. So that positive charge is indeed on the nitrogen atom, because a nitrogen with 4 bonds, no lone pairs, has a +1 formal charge. And lastly, we have an allylic carbonyl, and we're going to move the electrons from the carbon-carbon pi bond over 1, knowing that we can move the adjacent pi bonds, p electrons, out onto oxygen and generate a negative charge there. So this carbon that we took electron density away from, this carbon with a hydrogen there, here it is right here, and now it's electron deficient with 3 bonds, no lone pairs. So that's a carbocation. All right, so we've got net neutral on the left net neutral on the right.